So in this video, I'll discuss how to determine the density of a gas at STP. So before we get into the density of a gas, recall density is a characteristic that was discussed earlier in the course. Density gives us a quantitative relationship between the mass and the volume of a substance, and it can be shown by the equation D is equal to M over V. D represents our mass and M represents our mass and V represents our volume. And so now we can apply this property to a gas that is at STP. STP, recall, represents standard temperature and pressure. So under these conditions, our temperature is going to be 0 degrees Celsius, which we can convert to Kelvin, which would be 273. So recall, in order to convert from degrees Celsius to Kelvin, you simply add 273 or 273.15, and I'm going to just use the 273. But we have that temperature in Kelvin. And then the P represents pressure. So at STP, we have a temperature of 0 degrees Celsius and a pressure of 1 atmosphere. Also recall that when dealing with gases, we can observe various relationships between different properties by looking at the ideal gas equation. The ideal gas law equation, PV equals nRT, tells us that the product of the pressure and the volume is equal to the product of the number of moles times the gas constant times the temperature. And so if we use this equation, we can derive the density equation of a gas by rearranging our ideal gas law equation. So again, we know density is mass divided by volume. The ideal gas law equation does not give us a mass unit within the equation. However, it does give us volume. And instead of a mass, it does give us the mole, which we've learned and discussed previously, that if we know the number of moles of an object, we can multiply the number of moles times the molar mass, and that would tell us our mass. So remember, the molar mass tells us the mass of an object in 1 gram of that object. So if we know the molar mass, we know the moles, we can then use that to figure out the mass. So we can think about that since we need the relationship between the mass and the volume. We don't have it in this equation. We have the moles in the volume, but with the moles, we can simply multiply by the molar mass, and that would give us the mass relationship. So that means that we have to derive and rearrange this equation so that we get this relationship. So based on the ideal gas law equation, since I don't have mass over volume, I can rearrange it so that I have moles over volume. So I need my moles, my N, to stay in my numerator, my V, my volume, to move to the denominator. So what I'm going to do is remove the V from the left side by dividing by volume. And if I do it on the left side, I have to do it on the right side. So on the left side, they cancel out, leaving me with simply my pressure. On the right side, it leaves me with nRT, so number of moles times the gas constant times the temperature divided by volume. But again, I only need moles over volume. And so I need to get rid of my gas constant and my temperature. So I have to divide by the product of R and T. When I divide the right side, I have to do the same thing to the left side. So on the right side, R cancels, T cancels, leaving me simply with N over V. I was going to write it to the left, but I'm going to just keep it in the same order so I don't cause any confusion. On the left side, it leaves me with pressure times my gas constant times my temperature. Again, we're at STP, but this gives me moles per volume. If I need to figure out my mass, I still have another step that I have to take. And so when we look at this, in order to determine and convert my moles to mass, again, I have to multiply by the molar mass. So I have this ratio, moles to volume. If I want mass to volume, I need to multiply my moles per volume times the molar mass. So let's look at a clean slate. So I had I'm going to just keep it in the same order. P over RT. Then I had my moles per volume. But again, in order to get rid of the moles, I have to multiply by the molar mass. Of course, if I multiply the right side by the molar mass, I have to multiply the left side by the molar mass. So on the left side, because I'm going to end up multiplying, I'm going to switch to the units just to show. For N over V, we have moles over liters, but we're multiplying by grams per mole, which is the molar mass. So this allows you to see how your moles cancel. So on the right side, we would end up with grams per liter. Remember, mass per volume gives us a density. So by taking that ratio of our moles to volume and multiplying it by the molar mass, we would end up with our density for the gas. Our units are going to be grams per liter. However, if we go back to the right side and deal with that, again, we're at standard temperature and pressure. At standard temperature and pressure, our pressure is 1 atmosphere. That's a constant. Regardless of the gas, for any gas at standard temperature and pressure, your pressure is 1 atmosphere. But then I would be multiplying that by the molar mass. That will vary depending on what atoms and how many of each are present. Then I'm dividing that by the gas constant, 0.08206 liters atmosphere per mole Kelvin, times my temperature at STP, which is 273 Kelvin. So we can see how our units are going to cancel. We have Kelvin over Kelvin, atmosphere over atmosphere. And so if you put this in your calculator, of course, 1 times the molar mass is simply going to leave me with the molar mass. I'm going to just call this D now because that's going to give us our density. But 1 times the molar mass turns out to be just the molar mass. In my denominator, I have my gas constant times the standard temperature and pressure. This is going to always be the same product, which is 22.4 liters per mole. And so what we've done was use the ideal gas equation to derive how we can calculate the density of a gas at STP. So what it turns out to be is that for every 1 mole of gas, the density at STP is going to be equivalent to the molar mass divided by 22.4 liters per mole. Again, this tells us for every 1 mole. If we had more than 1 mole, then we would have to do more calculations, more conversions. But for every 1 mole of gas, the equation turns out to be your molar mass divided by 22.4. 22.4 is important because this is what's called the molar volume. Regardless of what gas, 1 mole of any gas at STP will have this volume, which is why it's the molar volume. This is the gas for each mole that is present at STP. So let's apply this to an example. So here it says, what is the density of oxygen gas at STP? So it doesn't tell you the formula, it simply gives you the name of the gas. It tells you the conditions, STP, because we're dealing with STP. We know the pressure, we know the temperature, we know those conditions, and we know that for every 1 mole of this gas, it's going to have a volume of 22.4 liters. And so based on this being at STP, we can use the equation we just discussed, where our density turned out to be equivalent to the molar mass of the gas divided by the molar volume. So that's 22.4 liters per mole. But we're dealing with 1 mole. And I can show per mole. And so we have to calculate the molar mass. So remember oxygen, we know that it's represented as O on the periodic table. However, you have to keep in mind that oxygen is one of the diatomic molecules, so it actually exists as O2. So we have to keep that in mind so that when we calculate that molar mass, we have to account for both of those oxygen atoms that are present. So each oxygen contains 16.0 gram per mole, but since I have 2 of them present, my molar mass is going to be 32.0 grams per mole. So in order to calculate this density, we have the molar mass, 32.0 grams per mole, and we have our molar volume, which is 22.4 liters per mole. So our moles are going to cancel out because we have per mole over per mole. And so once we put this in our calculator, 32 divided by 22.4, it gives us 1.43 grams per liter. So that means that the density of oxygen gas at STP is 1.43 grams per liter. So I hope this helps. If not, feel free to let me know. Thank you.